Bismillahirrahmanirrahim. Our today's topic is system of linear congruences. In last lecture, we discussed about the linear congruence, linear congruences. So today we will discuss systems of linear congruences, and here we will discuss uh, congruence with two or more moduli. For example, x congruent to a modulo some p, and or it's better to write ax congruent to b modulo p, and a prime y congruent to b prime modulo q. Okay, with two different moduli. So we will learn here that how to solve two linear congruences simultaneously in the system. Okay, so look at very easy example, simple example. So we have three congruences here. X is congruent to 1 modulo 3. Okay, and please remember that p and q are uh, primes, and a prime, b, and b primes are integers here. So x congruent to 1 modulo 3, x congruent to 2 modulo 5, and x congruent to 3 modulo 7. Okay, so we have a system of three linear congruences. So this is system of three linear congruences. Okay, so you can call it 1, 2, and 3. Okay, consider the first congruence. Consider the first congruence, x congruent to 1 modulo 3. Okay, and we know that it's very simple. You can write the solution. X is equal to 1 plus 3t1, where t1 is an arbitrary integer. Arbitrary integer. Okay, then put this value, put x in congruence 2. So let me write here. So congruence 2 implies, so by congruence 2, x is 1 plus 3t1 now. So 1 plus 3t1 is congruent to 2 modulo 5. Okay, so now we have a new congruence, linear congruence with variable t1. So you can solve this linear congruence for variable t1. Okay, 1 is here, you can subtract 1 from both sides, you will get 3t1 is congruent to 1 modulo 5. Okay, so because Z5 is a field, so every non-zero element of Z5 is invertible, so you can find the inverse of 3. So inverse of 3 is 2, because if you multiply 2 times 3, so here you will get 2 times 1 modulo 5. So 2 times 3 is 6, which is 1 in modulo 5. So we can write T1 is congruent to 2 modulo 5. So it's the solution of the second congruence for variable T1. So you can write T1 is equal to 2 plus 5T2, okay, where T2 is an arbitrary integer, just like the previous one, arbitrary integer. Okay, so now because equation 3 has variable x, so we have to convert this T1 in variable x. You can call that equation as equation 4. So put T1 in equation 4 to get the value of x in terms of T2. Now equation 4 implies x is equal to 1 plus 3 times T1, which is 2 plus 5 T2. Okay, so now x is equal to 1 plus 6 plus 5t plus 15 T2, or you can write 7 plus 15 T2. Okay, this value 7 plus 15 T2 could be replaced, okay, can be put in equation 3 or congruence 3. So put in congruence 3. Now by congruence 3, we can write 7 plus 15 T2 is congruent to 3 modulo 7. Okay, so in 7, so 7 is 0 here in modulo 7, because z7 is a field, so 0 of z7 is 7. So 15 T2 is congruent to 3 modulo 7, and 15 is 1 in modulo 7. So T1 is congruent to 3 modulo 7. So sorry, this is T2. So T2 can be written as 3 plus 7 T3, or better to write T 7 plus 3T. Now put this value in, for example, this is equation 5. So put in 5. So 5 implies x equals 7 plus 15 times 3 plus 7t, and this gives you 7 plus 45 plus 105 t, and this can also be written as 53 plus 105t, where t is an arbitrary integer. Okay, so if you consider 105, okay, that's the solution, that's the answer. But if you consider 105, so 105 is the product of the three moduli that is given here. So if you look at the three moduli, 3 times 5 times 7, and that's the prime factorization of the coefficient of t. Okay, so that thing could be used in uh, Chinese remainder theorem as well. Okay, anyway, 7 plus 45 is 52. Okay, so it's better to write 52 here. Next thing is the Chinese remainder theorem. The Chinese remainder theorem. This can also be written as CRT in short. Okay, so a statement: the linear system of congruences x equals x congruent to AI modulo mi, where where the moduli are pairwise relatively prime and I from 1 to k has a unique solution modulo m1 times m2 times mk, where k is a number of all i's. Okay, so the value of I is from 1 to k. Okay, so if you look at the solution of the previous system of linear congruence, so here we have uh, solution modulo 105, which is a product of all moduli here. Okay, so because these are all prime, so all primes, it means they are pairwise relatively prime as well, means their GCD their pairwise GCD must be equal to 1. Okay, now look at the proof of the theorem. So this proof consists on two parts. Okay, The first part, in first part, we have to show that how to construct a solution of the linear system, and the second part is related to the solution is unique modulo m1 m2 till mk, the product. Okay, so this solution has two parts. So first part is to construct a solution that will be helpful to solve systems of linear congruence by using CRT. So construct a solution to the linear system. Okay, we know that because all moduli are all MIs are pairwise relatively prime. Okay, so first we assume that let M, capital M, is the product of all moduli M1, M2 till Mk. So this capital M is the product of all. Okay, and now we and define capital Mi. It's the product of all moduli, means capital M, divided by the ith modulus. Okay, Mi. So capital Mi is the product of all moduli divided by Mi. Okay, and we know that all MIs are pairwise relatively prime. Okay, now if we look at the congruence, so congruence is X is congruent to AI modulo Mi. Okay, so here we consider the congruence Mi times Yi is congruent to 1 modulo Mi has a unique solution since GCD of Mi capital Mi and small mi is 1 because they are relatively prime. Okay, because we have already divided Mi by M to get capital Mi. So there is no Mi in capital M in capital Mi. So if we take the GCD of capital Mi with small mi, we get 1 here. Okay, because they are relatively prime. So if the GCD of capital Mi and Mi is 1, so it means this one divides this one. Okay, so it means the solution, so this congruence has a unique solution. Okay, and the unique solution, say Yi. So Yi is the unique solution. Okay, because mi is a GCD of small mi with capital Mi is 1. So there must be the inverse of capital Mi modulo Mi. Okay, so we must have the inverse. So say yi is a unique solution. Okay, yi is the unique solution modulo Mi. Now assume, let x, because we have to find the solution x here. So we assume that the value of x is a1, m1, y1 plus a2, m2, y2 till ak, mk, yk. It means we are writing the linear combinations of all yi, which are the solution of this type of linear congruence. Okay, so yi is the solution of this type of linear congruence. So here we are writing the linear combination of all yi's. Okay, so now we have to show that this value x is the solution of the system. It means this value satisfying all congruences in the system. Okay, so this can also be written in the compact form sum I from 1 to k ai mi yi. Okay, now take out any product from this. Okay, take out any product from this. So it means also x can be written as, for example, we are removing the jth term from this sum. So we can write ai mi yi and I from 1 to k, but we are not considering j when I is equal to j. So it means I is not equal to j. So it means this value cannot be equal to x because we have removed the jth term from here. So we must add jth term here. So this would be aj, mj, yj. Okay. So now let me write this equation in the linear congruence form. Okay, so x is congruent to sum, okay, sum of all values I from 1 to k ai mi yi and I is not equal to j plus aj mj yj modulo mi, sorry, mj, because we are taking I here. So mj. Okay, okay. So every term has mi. Okay, every term here has mi. For example, if okay, so we are considering mi means when j is not equal to I. Okay, and here we have j. So this is exactly mj, and here we have mj. So and mj. So the GCD of mj, capital mj and small mj is 1 here. So and m2. Okay. See all the sorry, this is mi. All the mi when j is not equal to I or I is not equal to j. So all of them are relatively prime to mj. So this can be written as sum I is not equal to j, ai, and the remainder will be 0. Okay. Here the remainder will be 0 when divided by mj yi. So modulo mj, because every mi, okay, every mi has a factor mj here. Okay, so this is completely divisible. Okay, so because we have removed mi from here, from mi. Okay, so ith term has been removed from here, but not jth, and I is not equal to j. Okay, so it means the remainder must be 0, because every mi when I is not equal to j has a factor mj. So that's why the remainder is 0 here. Similarly, aj, and because mj, there is no factor of small mj, so GCD of capital mj, small mj is 1. So here we will have 1 as the remainder. So yj times modulo mj. Okay. So this will be 0. We will only have here a j times, and we know that the congruence mi yi. Okay, mi yi congruent to 1 modulo mi. So we will also have 1 here. So aj times 1 modulo mj. So here we will have a j modulo mj, where j from 1 to k, any value 1 to k. Okay, so it means every congruence of this type, where the GCD, pairwise GCD of all moduli are GCD is 1, or they are relatively prime pairwise. So every system has a solution. Okay, so this is the solution. Okay, the second part of the result, to show that the solution is unique modulo m. Unique modulo m. Okay, so here we have to show that the solution is unique. It means if any other solution exists, so there will be no change in the solution as well. Okay, So for example, and how can we show the uniqueness? We will assume that there will be two solutions, and at the end we will show that they are same. So we assume that let x null and x1 be the two solutions of the given system. Of course, system of linear congruences. Okay. So it means we have to show that the two solutions are congruent, means x null congruent to x1 modulo mi or x1 congruent to x null modulo mi. Okay. Okay, let me open a different page as well. Okay. Okay, let me start from here. So because x null and x1, both of them are the solution of the given system. So if x null is a solution, it means x null can be written as, so that's a different page. Let, let me separate it here. So x null congruent to aj modulo mj and x1 congruent, because x1 is also the solution, this is mj modulo mj, and x1 is congruent to aj modulo mj for j from 1 to k. Okay, because we have this type of solution, and now we have to show that this solution is unique. So if both of them are written like this, x1 is congruent to aj modulo mj and x1 is congruent to aj modulo mj, so these two congruents can be subtracted. So this will be x1 minus x null, or x null minus x1, whatever, aj, or aj minus aj is 0. So that must be 0 here because we are subtracting. So 0 modulo mj. So this is minus. So now add x null both sides of the congruence. So that will be x1 congruent to x null modulo mj. Okay. Okay. So this is for j from 1 to k. Okay. Now we have x1 is congruent to x1 is congruent to x null modulo mj, or we can write x null is congruent to x1 modulo mj. Okay. So because this is a congruent, so if we apply the definition of congruence, we can write mj divides x1 minus x null, x1 minus x null for every j. Okay. So if mj divides x1 minus x null for every j, and j from 1 to k, means m1 divides x1 minus x null, m2 divides x1 minus x null till k divides x1 minus x null, and we know that all mi or all mj's are relatively prime pairwise. It means the product of all mj's, which was m previously, that we have already assumed here, m is the product, so it means m divides x1 minus x null. So if m divides x1 minus x null, so by using the definition of congruence, we can write x1 congruent to x null modulo m, and this shows that uh, the solution is unique modulo m. Okay, so x1 is congruent to x1. Solution, the solution is unique modulo m. Okay, okay, let's have an example. Okay, for example, we have a system. So this is example where we have a system of linear congruence as x is congruent to 1 modulo 3, x is congruent to 2 modulo 4, and x is congruent to 3 modulo 5. Okay, look at here, for all moduli, GCD of 3 and 4 is 1, GCD of 4 and 5 is 1, and GCD of 3 and 5 is 1. So GCD of all moduli or all mi pairwise is 1 here. So it means this system has a unique solution. Okay, this system has a solution and solution must be unique. So we will apply CRT, Chinese remainder theorem, to solve that. So here we have, okay, look at the solution. We consider m, which is the product of all moduli. So 3 times 4 times 5, which is 4 times 5 is 20, 20 times 3 is 60. And now we can find mi's. So m1 is m divided by m1, so it means 60 divided by 3, which is 20, m2, which is m divided by m2, which is 60 divided by 4, 15, and m3, because we have 3 moduli here, so m divided by m3, which is 60 divided by 5, 12. Okay, so now we have all mi here. So the solution is m1 y1 is congruent to modulo m1. Okay, that we studied in CRT. Okay, and m2 y2 congruent to this, there must be 1 modulo m2, and m3 y3 congruent to 1 modulo m3. So it means m1 is 20. So 20 y1, okay. So 20 y1 is congruent to 1 modulo 3, and Here we have 15 y1 congruent to 1 modulo 4 and 12 y1 y2, and here we have y3 congruent to 1 modulo 5. Okay, so we have these three equations by CRT, Chinese remainder theorem. Okay, so x can be written as the sum of all I from 1 to 3 ai mi yi modulo m. Okay, because we have only three terms here, so it's better to write them. Okay, so a1, so how can we find a1? So because this is okay. Okay, so we have first congruent, that is 20y1 congruent to 1 modulo 3. Okay, now so this can be written as okay, so we have these three moduli here, and we can write a1 m1 y1 plus a2 m2 y2 plus a3 m3 y3 modulo m. Okay, so we have all mi's. Okay, we have m, but we don't have y1 y2 y3, which are the solutions of these linear congruences, three linear congruences which are given here. Okay, and a1 a2 a3 are the coefficients. Okay, so it's better to find the solutions of uh, these linear congruence. Okay, you can call this equation as, oh, okay, it's better to write values here. So this m1 is 20 here, so 20 a1 y1 plus 15 a2 y2 plus 12 a3 y3 modulo, this should be written as small modulo capital M is 60. Okay, this is modulo. Okay, so let's try to find the solution of the three congruences. So 20 y1 is congruent to 1 modulo 3. So 20 is 2y1 congruent to 1 modulo 3, because 20 is 2 in modulo 3 and the inverse of 2 is 1. So we can multiply the inverse of 2 is 2 here. So we multiply to both the sides. We will have 4 here. So 4 is 1 in modulo 3. So that will be y1 congruent to 2 modulo 3. So solution is 2. Okay. Now the second one, which is 15 y2 congruent to 1 modulo 4. So this is 3y2 congruent to 1 modulo 4 here. So the inverse of 3 is 3 in modulo 4. We multiply 3 both the sides. So 3 times 3 is 9. 9 is 1 in modulo 4. So this is y2 is congruent to 3 modulo 4. And then in the last 12 y3 congruent to 1 modulo 5. So this is 2y2 y3 congruent to 1 modulo 5, because 12 is 2 in modulo 5, and because Z5 is a field, so every element has the inverse. So inverse of 2 is 3, so we multiply 3 both the sides. We will get y3 is congruent to 3 modulo 4. Sorry, modulo 5. And that's 2, sorry. We will have 2 here. Okay. So now we have solutions here. Okay, now we have all values that can be put here. Okay, let me use a different color. Oh, one more thing, because the inverse of 3 is 3, so 3 times 3 is 9. 9 is 1 here, and here we have 3, not 2. Okay, now we can find the value of x here. So a1, a2, a3, and y1, y2, y3. So a1, a2, a3 are given here in the question. So this is a1, a2, a3 are given here in the question, and now these are y1, y2, y3. So 20 times 1 times 2 plus 15 times a2, which is 2 here, 2 times y2, which is 3, then plus 12 times y3. y3 is a3 is 3 times y3. Okay, and then modulo 60. Okay, so x is 2 times 20 is 40. 15 times 2 is 30. So 40 plus 90. Okay, 15 times 30, 30 times 3, 90. Okay, 12 times 3 times 3, 9. 12 times 9 is 108. So this is 108 modulo 60. Okay, let me solve individually, because this is 30. Okay, modulo 90, modulo 60 for 90 is 30. So 30 plus 40 is 100. Sorry, 30 plus 40 is 70. 70 in 60 modulo 60 is 10. Now this will become 118, and 118 is 58 modulo 60. So that's the solution by using CRT. Okay, now let's discuss the general system. general system of linear congruences means system like x is congruent to a modulo m and x is congruent to b modulo n. Okay, where not necessarily m and n are relatively prime. Okay, so according to the result, this linear system is solvable is solvable if and only if and only if GCD of m and n divides a minus b. Okay, and if we have more equations, then we have this condition pairwise. Okay, and whenever this equation is solvable, so this system has solvable, so this system has a unique solution over the modulo the LCM of m and n. Okay, let me give an example for that. Okay, consider a system x is congruent to 3 modulo 6 and x is congruent to 5 modulo 8. And look at here, the GCD of 6 and 8 is not 1, so they are not relatively prime, but the GCD of 6 and 8 is 2, which divides the difference between 3 and 5, 3 minus 5. Okay, so it means this, so this implies system has a unique solution. So this system has a unique solution. Okay, so now how can we find this is unique solution? So look at here, the first congruence, which is x is congruent to 3 modulo 6. Okay, 3 modulo 6, and now because this is a linear congruence, so we can write the solution x is equal to 3 plus 6t square. 6t, let me write 6t prime with t prime is an arbitrary integer. Okay, okay, so put this, for example, this is 1, this is 2, and you can call this as 3. So put in 2 because you found this from 1, so put 3 or put the value of x in 1, put 2, so put x in 2, so we will have x is congruent, instead of x we write 3 plus 6 t prime congruent to 5 modulo 8. Okay, now subtract 3 from both sides, so 6 t prime congruent to 2 modulo 8. Okay, so now we divide because the common factor is 2 here, So 2 times 3 times p prime is congruent to 2 times 1 times modulo 8. So GCD of 2 and 2 is 2 and 8 is 2. So it means if we divide by 2, so we have to divide the GCD by, okay. So we have to divide 8 by GCD, which is 2 here. So we divide 2. So this will be 3t prime congruent to 1 modulo 4. Okay. This thing we have already studied. Okay. So now, because the inverse of 3 is 3, so we multiply 3 both the sides. We will get 1 here. So t prime is congruent to 3 modulo 4. So now t prime can be written as 3 plus 4 times t, where t is an arbitrary integer. Let me put this value, put t prime in 3. Now equation 3 implies x is equal to 3 plus 6 times 3 plus 4t. So x is equal to 3 plus 18 plus 24t. Okay, so in that case x is equal to 21 plus 24t. So that's the required solution, and this solution is modulo 24, okay, which is LCM of 6 and 8. LCM of 6 and 8. 6 and 8. Okay. Thank you very much. Assalamu alaikum.